Hello Internet. Today I have this 4090 from P&Y that came in for repair. Customer said it was damaged by some kind of a liquid, and now it's broken, and so is the customer's heart. Not to worry, I'm here to help. I'll get this thing fixed in no time, bringing the joy back to the owner's life. But first, let's look at how well P&Y makes 4090s. At first it seems obvious that the board itself is very small. Looking at all the cooling points, it appears to be well made, except the electrolytic capacitors were left on their own, which isn't the end of the day, but it could potentially prevent a blowout like this. The heatsink itself is really nothing to brag about. The copper tubes and the aluminum fins are not welded together. They appear to be just pressed in, which isn't the best way to transfer heat. But hopefully the size of the heatsink itself will compensate for that, as well as add additional weight to the card so it would crack in half. In comparison, let's look at our 100 years old EVGA 980 cooler. If we look close at where copper pipes touch the radiator, we will see that they're actually soldered together, providing better thermal transfer and longevity. And with that said, I honestly don't understand how these manufacturers get away with providing lower quality product at ever increasing prices. In any case, let's take some measurements, and I almost right away find 0 ohms and 12 volt connector. Okay, what I want to do now is to turn on the power supply, set it to roughly about 1 volt and limit it to 2 amps. Then I will run the ground wire to the ground end of the card and the positive to the probe, which I will use to poke around the card while looking for signs of thermal activity using my old Seek Thermal Pro, which by the way has become less and less expensive as other products have emerged. Before I start poking around, I want to make sure that whatever voltage we inject does not leak into the core. So I will test the voltage at the core while injecting the voltage from the power supply. I get 0.6 volt. Let's increase the amperage limit and see if that voltage rises. Same 0.6 volt. Great. Let's take the thermal camera and start aimlessly looking around in hope to find something unusual. And since I didn't find anything, I will increase the voltage and I'll double check the bleeding voltage, which is now at 0.9. We're still safe to proceed, but I do want to make the voltage higher and see if the voltage is increasing on the core or not. 3 volt on the power supply and the very same 0.9 on the core. Great, we're making progress. So let's hit it with 5 volt. 9 volt. And finally 12 volt is on the dial, but I will limit the amperage down to 1 amp. With no voltage leaking into the core, we're safe to proceed with the maximum voltage and the minimum risk of damage. It took me a few tries until I gave up and almost gave this card 6 amps until I noticed something was getting hot. Here it is. If we look close enough, there's a small sign of a blowout. So let's get this thing replaced and see if that helps. Driver MOSFET was replaced. Resistances are now normal. I'll go ahead and check everything else just in case so I won't have any questions later. And now it's time to address the liquid damage. I don't know what that liquid is. All I know is that it's clearly not synthetic. It's something organic because alcohol isn't getting it off, but soap and water does. Then I'll give it a job of blowing compressed air. You know, the blow job. And then back on the preheater to dry it out. And while the board is hot, I will reflow the area that was exposed to liquid to make sure that all the components are connected to their pads. Once that's done, I will power the board up, and it looks like we have a problem somewhere because the voltage keeps dropping every time I flip the switch. Armed with the thermal camera, I was set out to find another glowing component. And all I was able to find is that the two phases look different from the rest, so let's use an oscilloscope to look at their signal. I'll start at the bottom to get the baseline, and I'll mark every phase that I don't like the way it looks. This phase here looks like it has a lot of noise, but that noise can be generated by the controller. To confirm that it isn't, I will check the PWM signal on the first pin, and the signal is coming straight from the controller, and it looks fine. And that means we don't have a problem with the controller, but rather the driver MOSFET itself. So let's get this guy replaced and see if that helps. MOSFET replaced. No short circuits anywhere, so let's power on the card, and we get a result that's even worse than before. And now we have a short on 12 volt. Goodbye. So I've removed the MOSFET that I just put in, but the short didn't go away. And then I did what I did before. I was able to find another MOSFET right there, which just happened to be one of the prime suspects from before. So let's get this guy replaced and see if that helps. That didn't help. The short is still in the same place. So I went ahead and I removed the last suspect on the list, and even that didn't help. Continuing my search, I removed previously installed MOSFET again, just to verify that nothing was wrong with it to begin with. But without it, the card was behaving better. I ended up soldering another driver MOSFET on there, and it worked. Maybe I didn't have enough flux. Who knows? The important lesson here is to never power it on until you make sure that nothing was shorted. And in any case, it's all good now. I'll check all the phases just in case. Strangely, this driver MOSFET isn't working at all. I get the PWM signal from the controller, but it does not generate anything. I then checked the 12 volt rail one more time, and I noticed how slowly resistance value goes up. It should be at least twice as fast. So let's take a look at the signals one more time. Some of the MOSFETs actually look a little odd. I will go ahead and replace driver MOSFETs for both of the odd looking ones and see if that helps. Moment of truth. All phases now look the same, which is great. However, after all that work, I accidentally ended up burning the connector, which I'll have to replace later. Until then, let's boot this card and see if we get a picture. Great, we have a picture, and I'm very happy. All that's left now is to get the connector replaced, which will probably take a month to receive, so I'll see you later. And the connector finally came. Let's put this on and get this repair done already. This process proved to be very difficult. Heating the back of the board and pulling the connector through did not work, even with applying low melt solder. So instead of increasing the heat and damaging the board, I ended up breaking the pins one by one and pulled them one at a time. Clean everything up and put in a new connector. This card pulls so many watts of power that it causes interference on my HDMI switch when I try to record the screen. But otherwise it works fine, so we have a fix. And this is it for this repair. Thank you for watching. Please leave a comment, subscribe for more repairs, and goodbye.